So welcome to the Spark meetup. We alternate these meetups between the South Bay and San Francisco. Keep an eye on the meetup calendar. We've got 3 or 4 more in the queue, and they'll be going up in the next week or 2. Over the summer, we've been lucky enough to have volunteers for speakers and hosts to run a schedule about 1 meetup every 2 weeks. I help organize the meetups. I'm Andy Konwinski. I'm a co-founder at Databricks, and I've been helping run the meetup since the very first one, which is about 4 or more years ago. And we are on 35, 36 meetups now. So the space is beautiful tonight here at Galvanize, and we're going to hear a little bit more about the space first. If you have a space you'd like to host a Spark meetup in, let me know afterwards, and we always need people to volunteer to host these meetups. And in exchange, we give you an opportunity to have a shout out about what you're all about. So let's hear that about Galvanize now.
Is it on?
Thank you very much. Hey everybody, just want to quickly welcome you to Galvanize. My name is Michael, oversee event strategy here for us. You are in one of our 6 campuses that we have across the country. Inside of our campuses, we have formal education programs in data science and full stack web development. So a 3-month immersive in data science, 6-month in full stack web, and then also a 1-year master's degree that you can earn right here in this building in data science. So if you know anyone who's interested in anything like that, please send them our way. Beyond that, we also have 200 startups that work in this building every day. So we have a shared work experience as well. And when you become a member and work from Galvanize, you gain access to mentor programs, great conferences, discounts on events, and just great educational content. Beyond that, we also love to host events. So if you have any tech or entrepreneurial related content that you'd like to host, we'd be happy to have you here. Just let us know. All in all, Galvanize is a tech education company where people come to level up their skills, their knowledge, and their network. So thanks again, and very happy to welcome Databricks here tonight and all of you. Hope the pizza's good and hope the content's better. Thanks.
And while I'm with Databricks, this meetup is all about IBM. So I'm happy to announce or introduce David Falside, who's a team lead at IBM, where they've been working with Spark for a year or 2 now. And IBM has been making some amazing announcements in the last couple of weeks that you've all probably heard. And we're going to hear a technical deep dive tonight. And David's going to tell us a little bit about the group and what they've been working on, and then introduce our speaker. So let's welcome David.
Thanks, Andy. My name's David Falside. I'm a team lead in a group in IBM called Emerging Technologies. Our mission in life is to identify new technologies and to work with those technologies, work with customers, validate the ideas sort of that are inherent in those technologies. We've been working in and around the Spark space for a year or 2 now. We're particularly interested in enabling line of business kind of users, data scientists, to take advantage of the fairly unique capabilities that are provided by Spark. And the work that Chip Senkbeil, my colleague, is going to talk about comes out of that work. He's going to go into the sort of the technical details of the Spark kernel. Which comes out of our work and really has enabled us to enables applications for the line of business kind of person. The technology Chip is going to talk about is currently available on GitHub, and we're looking to contribute it to Apache. So without further ado, let me hand it over to Chip. Thank you.
The magic microphone thing. So how is everyone tonight? Doing well? Enjoying the pizza? Yeah? So like David said, my name is Chip Senkbeil. I'm a software engineer at IBM underneath the Emerging Internet Technologies group. So today, or tonight, I'm going to talk to you about the Spark kernel. It is what we at Emerging Technologies and IBM feel address one of the problems we ran into when trying to work on some of our prototypes. Emerging technology, we make prototypes, get customer engagement, and then we feel they're going somewhere, we hand them off to product teams to develop. So yeah, I'm going to talk to you about Spark Kernel, show you kind of the scenario we went through, what problem we encountered, why we think this addresses it, and then what other functionality this gives you on top of Spark. Okay, so outline basically, cover scenario, problem. The problem itself, spoiler, is how do you enable interactive applications against Apache Spark? We went through quite a few different trials until we finally made the Spark kernel. And then, of course, I'll describe why the Spark kernel is the answer to this problem, along with the architecture of it, a memory issue we encountered, and then I'll talk about a Comm API, which is an additional component of the Spark kernel. Then I'll give you a few demonstrations on top, live sheets and a RESTful server. Both of these run on top of the Spark kernel. And then finally, I'll end with some ways to extend it that we're working into in the near future, and then, of course, summary and questions. Okay. So when we first looked at Apache Spark, we saw that it was gaining a lot of momentum, and we thought, okay, this is very good. We want to try to explore the space. And we already had a prototype called Live Sheets. It was a line of business tool for data exploration, data analytics, and it was running on top of Storm. And so we wanted to try to port it to Apache Spark, and there are some things we needed it to be able to do on top of Apache Spark that we were already doing on top of Storm. We need to be able to build different computations to compute on the fly. We need to be able to do these computations on static data and dynamic data, so your historical data, your streaming data. And of course, we need to be responsive. This is supposed to be a data exploration tool, so you don't want to sit there for minutes waiting for one of your queries to come back. You get easily bored. It just becomes very frustrating to work with. Okay, so problem was there were quite a few different ways to interact with Spark. So we started looking through trying to figure out, okay, what way can we use that's going to be the best way to interact with Spark? We need to be able to give quick queries, do computations. What options do we have? Now, we were looking at this during Spark 0.9.1 and the 1.0 transition, so it was quite a while ago. But most of these options, in fact, all the options I think were already available. I think the JDBC might have been under Shark instead of Spark SQL at the time. But there were 4 options. Spark Submit, the most advocated of Apache Spark, a shell script you run. It submits jobs to the Apache Spark cluster to run. Then you have JDBC, ODBC, right? So you stand up Spark cluster, Spark SQL. There's a server that runs that you can connect to, perform all those kind of database queries. You've got RESTful interfaces, right? So you want to submit some jars. You can just post them via REST. They will get started, run, give you computations, and you can even get the results back via REST, which is pretty nice. And then lastly, you have kind of the oddball of the group, the Spark shell and its derivatives, PySpark, and the R one now, I believe, with 1.4. And it's interesting because it's got the most flexibility in the fact that you can basically write any code you want. It'll be run as your driver application and get evaluated, and you get results back. So it's pretty neat. But unfortunately, the Spark shell is the most limited in the fact that there's no service, no API available. It's just a shell. So in the end, we tried to use Spark Submit. And we were like, OK, let's use Spark Submit. We'll bundle up all of our computations into these jars. We'll start an external process that's Spark Submit, try to get it to use that jar on a Spark cluster, and then we'll go from there. And so each time in our application that someone changes a query, we have to rebundle the jar, ship it over, and it took quite a long time. There's quite a lot of overhead in doing this, by the way. So there are a lot of problems. What was wrong, really? So like I already said, you had to rebundle the jar every single time you wanted to change your computation. Change a query, change an RDD API, anything, you had to rebundle this jar. Not the best process. It also wasn't the easiest to be able to attach to this computation running in a Spark cluster. The most feedback you could get was if you had a problem, go look at the Spark logs. And then lastly, of course, the results themselves. You get your computation, it works. Well, how do you get the results back to your application? You had to do something like write out to a data store, HDFS, Postgres, Cassandra, one of those options. And then you had to bake into your application how to read out of the data store and be able to get your results. So you're already forcing your application to conform to some sort of data store, or have to write your own abstraction on top. And so overall, it's a very slow turnaround. We already ruled out one of our designers, which was we wanted to run in seconds, not minutes. And it was taking minutes to be able to deploy, get results, and it became very convoluted. It was not the most ideal scenario. So enter the Spark kernel. So this was inspired by the Spark shell, which basically is a REPL. For those of you that are not familiar, a REPL basically allows you to enter code. It stands for read, eval, print loop. You basically read some code, evaluates it, prints out the result, repeats. And so we thought, oh, that flexibility is really nice. We like being able to submit arbitrary code and be able to evaluate it. I want to do a reduced job, I can. I want to use Spark SQL, I can. I want to do streaming, I can. I want to use MLlib, I can. It was the most flexible option we had available. So we basically wanted to expose a remote API on top of the Spark shell. That was the original goal. We want to make it interactive, and to do that, we're going to provide a remote API on top of a Spark shell. So the kernel itself, the little red square here, stands where the cluster is. So you have the cluster, you have the kernel, and then you have this line, which stands for your firewall, wherever your cluster is running, and then your applications, and then IPython, which I'll get to in a minute, are somewhere else. They can connect remotely. And what the kernel offers is being able to execute the raw Scala code like we wanted. You can submit Spark jobs via code snippets or jars, just like we wanted, so we have both options. And then you can get the results directly into the kernel and fed back to your application, which is something we wanted. Now, of course, you can still write it out to data stores. It's a matter of sending code snippets or jars. But you also want to be able to get this feedback back directly, like the RESTful server offers or the Spark shell offers. So other benefits. So in our case, when we need to have very dynamic, flowing type interaction, it avoided all the friction of shipping these jars and having to read results from a peripheral system. It made it really easy. Just boom, I do a reduced job, I get the number 55. There you go, that's my answer, right? Well-defined API. So I haven't touched on it yet, but the kernel itself is built on top of the IPython, now known as Jupyter, message protocol. Raise your hands, how many have used IPython or at least know what it is? Yeah, so quite a lot of you. So a little background as to why it's well-defined. So IPython/Jupyter is on their fifth iteration of this message protocol. So it's had quite a few iterations to get through. It's language agnostic now, which is wonderful. And it's actually more flexible than you might think. It's not just about execute code and continue. And you'll see that when we get to some of the discussion later. Third, as I try to hint out here with the here's your cluster and the kernel, and then there's a line, and here's where everything else runs remotely, the kernel serves as a proxy. So for those of you that aren't too familiar with how a Spark driver works, which is what starts your Spark context and submits your jobs to a Spark cluster, it needs to have access to all the workers and the master of your cluster, which means there are a lot of ports being opened. There's a lot of potential shakiness about the security. It's a bit of a problem if you want to try to run it not in the cluster itself. So to get around this, one of the bonuses is if this kernel serves as your main driver and just accepts code snippets, jars, and other interaction to use your Spark cluster, then you can basically proxy and only open up the ports the kernel needs and not expose the rest of your cluster, which is in fact what we do today through Mesos and other options. And then finally, we already provide a client library. So this is something I have not seen with other projects out there. For our prototype that we're using, called Live Sheets, it actually uses the client library directly, along with some other demos I'll show as well, pretty extensively. So it's been pretty thoroughly used. And it just means it's a lot easier to immediately jump in, and once you've, say, written some snippets of code that you like and want to try using and embed into an application, you can hook it up to this library, and you immediately have an application that's using Spark with those code snippets. So I'm going to jump into the kernel architecture. So this is the summary of the architecture. It's got different layers. I'm going to go through each one. It's not very scary. In fact, you'll think, man, this is so simplistic. I could have done this in my sleep. Maybe you could have. But yeah, so I'm going to go through each aspect of this. But first, I'm going to answer two different questions that might pop up. So ZeroMQ is one of them. People might say, why are you using ZeroMQ? Why not REST? Why not WebSockets? So one aspect was we liked IPython notebooks a lot. We didn't want to break the experience of, I want to use IPython, write some snippets of code, see what works, and then once I've gotten a notebook that works, I want to be able to use it in an application. I want to be able to deploy this long-running application that can use the code I've already written. I don't want to rewrite a whole new application that takes something that I've written in snippets and have to do it all over again. So IPython compatibility was pretty nice, and IPython itself uses ZeroMQ as its communication. Responsiveness. So ZeroMQ is actually very responsive, and the model it's got is pretty strong for a lot of messages back and forth, and it's actually got what I consider behavior patterns that allow it to be a lot easier to develop. So you use something like WebSockets, you have to write all of it yourself, and you have to go through some HTTP type stuff, use REST, and you have more sluggishness, and it doesn't really conform to what we needed, which was interactive. So interactive with this behavior, for example, if I make a publisher and a subscriber, that's two kinds of ZeroMQ type structures. The publisher sends a message, all the subscribers immediately get the message. There's no need for me to re-implement all that kind of logic through some code. It's just baked into their type of design. So that was actually pretty nice in itself for a lot of our type of structure that you'll see that we're using when I get down the line. The next question is why akka? So how many of you know what akka is? A few hands, a decent number of hands. So there are quite a few different reasons why we liked akka. They follow Erlang's type model, actors. That is concurrency. You have a bunch of actors that float around. You can send them messages. It avoids concurrency problems by having these messages basically wrap all the concurrency. You don't have to really worry about it. It's typically immutable, the messages. So you don't have to worry about the state getting mutated when you're passing it through. So one reason was concurrency. You use akka, you don't have to really think too much about concurrency. It just happens naturally. So we can handle concurrent connections on the kernel, and a lot of other issues just go away. Code isolation. So one aspect we wanted to do is we wanted the kernel to be pretty easily extensible. So what you'll see if you ever look at the code itself is that each component, interpreting code, performing inspection on RDDs, other interactions like that, are each isolated to their own actor, which means that each actor has its own job. It means that it's easy for someone else to come in and say, hey, I've developed this new feature. I want to pop it into the kernel. In fact, that's what we've done over time. If you look at our commit history, you'll see more actors pop up without having to break the general flow of our designs. The architecture hasn't changed much since it started in July of last year, I think. Fault tolerance. So akka and Erlang that it's based on are really known for their fault tolerance. You have problems in your system. They do what's called a fail-fast type system. So your actor that, say, is evaluating code suddenly has problems and runs out of memory. It dies. Your whole system does not die. It gets restored back from where it was and can continue like nothing ever happened. It's a very nice, very robust system. In fact, Spark uses it underneath, but I don't know to what extent they use things like fault tolerance. And lastly, scalability. So these actors, you implement an actor that has a certain role, such as interpreting code, and say, okay, you have this out in production, and you have 10,000 people trying to interpret code at the same time. That's not a very good idea if you're going to have, say, one point to interpret this code. So with akka, it's actually trivial to scale out any of your actors to have round robin or some other effect where basically you go from having one person serve this request to, say, 1,000. And it's pretty simple to do, so you don't have to really change any of your models. So the thought would be, as we're going and using the kernel with our applications, if we see a certain point that's a bottleneck, we don't have to really worry about, oh, we have to redesign our whole architecture, just scale out the actors. So channels of communication. You've probably seen this and you say, what are these 5 things at the top of this architecture? So I'm going to go through all 5, but before I do that, I'm going to explain what's defined these 5. So I mentioned IPython protocol, which is what we're basing all of our messages off of. And IPython specifies incoming and outgoing messages that it handles, and also needs 5 channels of communication. These are 5 ports they open that handle different parts of what a kernel should do and how it should respond. And of course, following IPython ZRMQ-based structure, each of these 5 is a port or a socket that's open using ZRMQ. And ZMTP is the wire protocol used. But actually going into these, so the first 2, we have heartbeat and we have shell. Heartbeat, as you might think, is basically just to let you know that the kernel is still alive. Very simple. The only reason it's got its own socket is to avoid any slowness with you flooding a socket with messages or queuing up messages. It's designed just to, you send a request and it responds as fast as it can with the exact same request, so it echoes out your message. That's what IPython uses for all of its backends. The Python one, the Haskell one, the Ruby one, all of those use that kind of logic to keep the kernel alive, to ensure that's alive. The shell is one of the main 2 ports you should care about. If you're going to care about any of the ports here, the 2 main ones are shell and IOPub, which I'll get to. The shell is what's used whenever the client wants to issue a request. So the client says, hey, execute this code for me. The kernel says, sure, I can do that, and that's done through the shell. And so code execution, along with the comm messages, which I'll get to later, are the 2 main types of messages that are sent to this kind of channel. And then you've got control and you've got standard in. So control is basically just a shell, but higher priority. So if you want to do shutdown messages, interrupt code, stop a job, any of those kinds of interactions, you typically want to go through a different port to avoid flooding the network traffic, to avoid your program itself from queuing up too many messages and not getting to your action soon enough. That kind of thing. And since you're using akka underneath to handle the concurrency, you'll get this message and process it right away, and not have to worry about, oh, okay, my program's slowing down, it's getting a bottleneck somewhere, and it won't die, or get restarted, right? And then standard in is the opposite of the shell. So whereas the shell is doing client to kernel, standard in is doing kernel to client, or clients, could be more than one. We haven't really used this too much, even though it is in our client API, but you'll see it for things like when you use IPython, if you try to read from standard in, typically IPython will open up a little text box in their UI, and you enter some text, and that gets sent back to the kernel. So typically this is the form of the kernel says, hey, you've told me to do something, but I don't have enough information. Please enter some more. We have some ideas of what we want to use this for later, but that's just part of the IPython's protocol and what they need. Last one is IO pubs. This is one of the most important ones. Whenever you have any kind of side effect or comm message or other kind of message that needs to be broadcasted, the IO pub is example of the publisher I was mentioning earlier, and for every client that's subscribed to the kernel, it'll publish out the message. So it's a fairly easy way to broadcast messages to all the clients listening. You can broadcast the state of your cluster with the Spark context. You can broadcast the state of messages that need to be sent across everyone if you want to synchronize data. It's a pretty nice way to handle it, and it works flawlessly. Okay, so I've discussed how messages kind of come in and the kind of the ports and where they kind of flow. Well, let's get into how you actually handle this layer, which is the parsing and the validation. So we use GROMQ underneath. We previously used a version of the native libzmq. But now I use GROMQ because it's pure Java. It actually has better performance than the version of ZROMQ we're using and has other benefits as well. But we're using GROMQ to get the messages and send them out, but we've abstracted that with ACA actors. So you don't actually have to worry about what protocol you're actually using underneath. For all intents and purposes, when the kernel gets to this point, it sees a message as a message. The flexibility of this is you could easily replace GROMQ with, if you really wanted REST, you could try to do that. If you wanted WebSockets, you could do that. If you wanted some other form of communication, you could do that. It's a pretty easy way to drop things in by merely replacing this ACA layer of the message parsing. The other aspect is something that IPython enforces, which is, it's their only real form of, I'd say security. I wouldn't really consider that much security. It's more just a validation of your message. They pass in signatures that are keyed hash message authentication codes that they use to generate. They use SHA-256 digest and all that kind of stuff to basically create a signature that's going to match the signature they give you. So you get a message, has a signature, you have to produce the same thing from the message, and if they don't match, then there's some sort of problem. The secret key that you're given is when the kernel starts up, so you can give the kernel whatever secret key you want to ensure that no other client that you don't know of is communicating with you, as well as just ensuring that there's no corruptness in your data. So routing, fairly simple layer, still uses ACA actors. You send a message to the routing layer, it determines based on the type where to go. So you can imagine if you're getting a lot of messages, you might want to scale this layer out and have multiple actors that are handling the same kind of logic. But all it does is if it's an incoming message, it's going to hand it off to the handlers, which are the next thing we'll get to. If it's an outgoing message, it'll say, okay, this needs to go over the shell channel, or it needs to go to the IO pub channel. It'll determine which one to go through. So you don't have to think about in each of your handlers or each of your individual logic, where do I send this to? You just think of handling that specific piece of code, and when you send it to the routing layer, it'll take care of it for you. And finally, the message handling. So this is where we have the more specific, for each task the kernel needs to handle, it's going to have a different handler. So in this case, let's take an example of the interpreter. You want to interpret some code, like the Spark shell, for instance. You send some code. It gets routed, and it finally gets to the execute request handler. So what this handler will do in this case is it'll actually do the child actor bit, but it'll receive the message and process it. So in this case, the interpreter actor, we follow something that Erlang's pretty good about, which is called the error kernel pattern. There we go. Tough to say. But anyway, the error kernel pattern is basically this philosophy of if you have state that you really care about, you don't want to do operations where that state is. Reason being, if you have major failures, you're going to lose your state. Very bad, right? Especially with long-running applications. So the idea of this pattern is whatever's holding your state, in this case an actor, you want to create child actors that's managed by this stateful actor that will do all the jobs. So in case of an interpreter, the interpreter is going to hold the state of just that, the interpreter, any code you've evaluated, any Spark-based computations you've done. But in terms of actually evaluating new code, looking up data, any of those kind of interactions will be done by child actors. And so if those fail, get restarted, no problem. You don't have any corrupted state. But if the main actor did fail, then you'd lose your state. So this is an idea of protecting that kind of state from getting lost. It also reduces the strain of the handler. But once again, strain, not too big of a deal, because you can always scale out your actors as well. So let's get into what is actually doing the compilation and execution of all this code you're sending. So we're using the same API that the Spark shell is using. The Spark shell itself is using what's called the Scala REPL. They have an API to be able to compile and execute code. But they've modified it a little bit to be able to better serialize all their classes they're generating, ship over to a cluster. So normally, if you write Java or Scala or any JVM-based language code, and you're compiling it, most of that code cannot be shipped over the wire. It cannot be transformed into bytes and shipped over unless you mark it explicitly as serializable. So Spark's done a little work to make their code more serializable, be able to be shipped over to the cluster. So we're taking that API, putting it in, and that's what serves as our interpreter. It compiles the code and executes it. So it's more of like a pseudo interpreter because it is still, let's say, compiled language. So there's 0 modifications to this. It behaves just like the Spark shell would, which means that anything you can do in the Spark shell, you can also do in our Scala interpreter. The difference is that we expose a few more variables. So if you've used the Spark shell, or maybe the PySpark one, or maybe the R one as well, they expose a few of the standard contexts. They'll expose the Spark context. They'll expose, now they'll expose a SQL context. Sometimes they'll generate a Hive one for you if they can. And so we do something similar. We'll embed magics. For those of you that are in IPython, you should know what magics are. They're basically pseudo strings that do fancy operations. In our case, things like adding dependencies or visualizing RDDs and that kind of stuff in a notebook. But along with that, it also does comm communication, which once again I'll get to in a little bit. But so basically, for all intents and purposes, it's just an ACA actor that's wrapping the Spark REPL, Spark shell, and the Scala REPL underneath. And so for those of you that aren't familiar how the Spark shell, the PySpark shell, the R shell get their magic done, there are two things they do. One, the main one, they stand up a class server. Just like if you do a Spark context.add_jar or any of the other forms, they have a class server that's going to serve all the class files that are generated when you use the REPL. You do in Spark shell, you do sc, parallelize, 1 to 100, reduce, blah plus blah. That gets compiled down into quite a few different JVM-based classes. So obviously, the cluster doesn't know about these classes except for the fact that a class server is stood up that hosts these class files. So whenever you make a request on the cluster and it says, I don't know where this is coming from, it'll check not only your Spark context class server, but also the REPL one. So you basically have two class servers stood up now. And Spark Scala 2.10 version, they actually bundle the HTTP class server with their REPL. So as soon as you start it up, it starts with the class server. 2.11, it's separate now, which is a better idea. The other thing is, of course, we provide the Spark context, like I hinted about with the variables earlier, because you need some way to actually do your Spark operations with this code. You can't just write 1 + 1 and say, Spark, go do 1 + 1. You have to actually tell it through maps and reduces and other operations. And of course, we expose this in the same way that the Spark shell does, which is through a name called sc, but it can be done through any other form as well. So client architecture. So I mentioned we have a client library, which basically is a mirror of the kernel library. It has the same kind of flow, gromq to receive messages, ACA actors to kind of abstract away that process. It goes through the same parsing, validation, routing, handling, all that kind of stuff, which means that we're reusing most of the code base. There's actually not that much logic additional in the client library. And of course, we expose how you interact with this kind of API through a few methods, which you'll see in actually the next slide, to execute code and do other interactions. So all of you kind of have a glazed look. Let's get into some fun stuff. So this is some code. We're not going to stay here long. This is what it would look like if you wanted to do a quick Spark execute code and get a result back. In fact, there's more here than you don't really need to care about. I'm showing creating the client. It's actually a lot easier than that now. This is a little bit of an old snippet of code. Executing the code itself, I'm just doing a parallelize and reduce. Notice how it's in a string. There are plans in the future to make it more error checking at the compile stage. And then you have two things I'm doing here, results and error. So if you get a result back that's valid, you can print it out. If you get an error, it'll print out the error. And we'll see that in the demonstration that I've got now. So what I'm going to do here is I'm in a notebook. It's running a Spark kernel, but I'm going to do something a little weird and add a client library to it. So I'm adding the client library, and I'm connecting to a different kernel. And so what I'm going to do here is I'm going to execute this sc parallelize 1 to 100, reduce the numbers together. I'm basically going to add all the numbers 1 through 100 together. The most exciting thing you can do with Spark, I know, it's so thrilling. But yeah, so it gives you the answer 5050, not that exciting. Now I'm going to demonstrate an error. So the error itself, something trivial, but any error you get gets handled this way. It gets passed through a different callback, same thing that you'd see in something like JavaScript. The last thing I'm doing is to just demonstrate a different way. If you're getting streaming data, in this case I'm just doing print lines, because right now I have it enabled to treat standard out and standard error as streaming messages. You can turn that off. And so as you get those messages, you can see that I'm getting the data back. So pretty simple to do. Really small, tiny APIs. And that's for executing code. So far, I've been talking about executing code. Executing code is amazing. I love it. You want to execute code? You want to? We all want to execute code. I know. But you don't. You don't want to execute code. Why? There's a huge memory issue with the Scala REPL, and in turn, the Spark shell. If you use it long enough, it will die badly. Why? Because the way the Scala REPL is designed is that whenever you want to run some code, it has to compile it. Whenever it compiles it, that means generating new class files. And unfortunately, because it's a REPL, and there's no concept of giving back variables you've created, there's no concept of something that's not global when you're using this REPL, everything stays around in memory forever, which is a bit of a problem. You compile a code, and it's going to generate more class files. It's going to load those classes into the JVM. The JVM is eventually going to run out of permgen space. Now, think if you're using JDK 8 or above, they've gotten rid of permgen space. It's all one memory, but you're still going to run out eventually because they're never given back. So if you pull up the Spark shell and you just keep doing like 1 + 1 over and over, you're going to run out of memory eventually. It'll take quite a while. We've done some tests on this. If you somehow got around that, the next problem is that even if you got rid of the class generation problem, the Scala REPL, and in turn the Spark shell, holds any state that you get. 1 + 1 assigns it to a variable. Doing more complicated computations assigns it to a variable. Holds all of that in state. They have these request classes that they instantiate. They hold state. They hold the bytecode that you generated, all this kind of stuff. And it sits around forever. And so eventually you'd run out of memory because of that as well. So there's a bit of a danger in using the REPL in its current form without fixing the problem, or at least mitigating it. So we're going to go into what mitigates the problem for us, which is the Comm API. The Comm API is another part of the IPython protocol that some of you may have used if you've used widgets at all in IPython. How many of you have used widgets? No one. So any kind of user interactive thing that connects to the kernel and behind the scenes uses these kind of Comm API type things, right? So the Comm API is a way of IPython to synchronize data, their way of synchronizing data between a front end and a back end. But we can use it for a lot more than that. So what I'm going to jump into is kind of what you can do with the Comm API, what the individual pieces are. They're actually pretty simple. And then you'll get to see some demonstrations, and as we see them, I'll also explain how we're using this API along with the code execution API to have a very interactive application without hitting problems like out of memory. So first of all of these messages, the open, the message, and the close, are bidirectional. They can be started by either side, the front end or the back end. And you can programmatically add them. So you start up and you don't have the messages you need, you can add them programmatically through an API we expose, meaning that you can add messages on the fly. If you wanted to find messages in the middle of your application, you can. If one application varies from the next one, you can add APIs depending on what application that you're building. So how does this actually avoid the problem? So first of all, when you're defining these messages, you're only going to compile once for these messages, and you're never going to recompile when you say want to run the same code over and over. What you might want to do is something that's just, say, running some streaming job and wants to check it occasionally, or some other interaction. So you're avoiding recompiling, and you're also not keeping the execution state. So before, we were creating these request classes. They're holding the values of something you were doing. This is just going to call some callbacks, so you do your action based on whatever you get, and then you're done. You're not going to hold on to anything. So it basically removes any kind of global state that might hang around. And of course, it's simple. There's only 3 types, and you could think of them the same as you would any kind of writer and basically any API. You open, like for a file, open a file, write some stuff in it, close it. Start communication, send some data, stop communication. It's very simple. So now I'm going to just kind of go through each one, and then we'll see a little demonstration of what I'm talking about so you don't think I'm crazy. So open, right? So open, all it does is you open from either the kernel side or the client side, and it just says, hey, both sides need to now start listening for a specific ID, this ID here, this Comm ID, and whenever you get one of those messages, I want to interact with that kind of message. And you can include startup data as you need in a JSON-type structure. So typically, the IPython protocol sends messages via JSON, but in terms of 0MQ, it then converts the JSON strings to byte strings and passes around byte strings. But the API itself is JSON structure. So you start this open. You're going to say, I'm going to start sending messages, and now you want to send messages. And they're even simpler. You basically specify the ID that you want to use, the ID that you already specified during your open. You send some data, and the other side should handle it appropriately. That's all that it is. And the last one, closing, once again, very simple. For something that you've already opened, you can just close it by specifying the ID and give some optional data in case you want to handle some sort of special teardown scenario, right? So it's just a simple case of I want to send arbitrary messages. You can define how they're handled by the data that you're providing. So now we're going to jump into a scenario here. So on this side, this is a remote kernel I've got and a notebook. And all I'm doing is I'm defining some handlers. And these handlers are going to handle an open request and a message request. When I do an open, I'm going to print out a message saying I received a connection, and then I'm going to send a message back saying, hey, I opened the specific message that you sent me. For the message handler, it's going to check to see if you sent it a message containing the keyword closing. And if you did, it will close the state. If not, it'll keep it open and just print out whatever you sent and echo it. So we have a very simple case. You send this remote kernel an open, it'll send back, hey, I opened it. You send it a message. If it doesn't have the name closing in it, it'll echo the message back. If you send a message that has closing in it, then it'll send a message back saying, hey, I'm closing you, and then it will actually close itself. So on the other side, this is a different notebook that has the client library in it. It's actually the same one you saw earlier that I was doing the code execution in. I'm registering some other handlers. So I have handlers on the kernel side. I have handlers on the client side. Think of them as JavaScript callbacks. And so in this case, whenever I get a message, I'm going to print it out. If I get a close, I'm going to print it out, just to show that I'm getting messages back and forth. So next, I'm going to start by opening. So I'm going to initiate an open from the client side. You can do this on the kernel side as well. And you see that I immediately got this message that says response opening my message type, which is something I said would be printed off when I got it. And then on the opposite side, I get the received connection. So got a connection, printed it out, great. It ran that code. That's all that it mattered, or that's all that it did. And it's all compiled because you compiled it once and it's going to re-execute it over and over. So same kind of situation for the message. So I go back and I say, okay, now I want to send this message, Spark Meetup, right? I send it, it gets echoed back to me as I would expect. When we go to the other side, you'll see that it actually printed out the message as well as saying it's incoming data, right? So once again, very simple. Already using compiled code, no need to recompile. And then finally, the last case, I'm going to send a message that says closing in it. I should get a closing done, which I do. And then when I go check the other notebook that's running the remote kernel, you'll see that I got the closing message on that side as well, and it executed the final bit of code. Very simple API. Could obviously be expanded, or maybe higher abstractions on top, because it's pretty low level. I like to think this is the lowest level of transportation you could use. But it's a way to take advantage of cases where you want to define a message that does an operation. Maybe you want to send some data that tells you, I want to do a map operation, and here's the kind of work I want to be done, right? You could put that in a message and then just send it via the Comm API. It evaluates it and sends you back some JSON data. There's a way to kind of define operations you'd normally rerun fairly easily without having to send code snippets over and over and over. And in fact, you don't even have to define it through the kernel itself. You can define it on startup by adding some jars, right? So that was a rundown of the APIs that the kernel exposes. It's got code execution, it's got Comm. It's actually got a lot more than that. Those are the two main ways that we communicate data. And the reason I picked those two to discuss, because those two are used hand in hand with our demonstrations such as live sheets. Now, I mentioned in the beginning, but live sheets is a line of business user tool for data exploration and data analytics. So it's meant to be a higher level tool. We've got a little DSL on top that will be generated. But it's a higher level tool that uses Spark to basically explore data. So you're going to kind of see an example here. So what I'm going to do is Nitro is our main group name here, so live sheets is part of it. And I'm creating a document. Live sheets is document-based. I'm going to call it my Spark Meetup. And I'm pretty slow at typing, so I'm going to accelerate a little bit of this stuff so that it gets a little bit faster. But basically what we're going to do is we're going to load up taxi data for New York and New Jersey. We're going to inspect it. We're going to see how many people were picked up at locations, how long did it take to get from point A to point B, what was the distance they traveled. You can imagine this would be useful for people that want to, well, for taxi companies that want to see, where are the hot spots, where should taxis be most of the time. So we've loaded some data. It's just a table format, pretty simple. And we're looking at passenger count here. That's what I'm scrolling over to. So this shows you how many passengers were in the taxi when it left, right? So we got 2, 1, 3, there's more of them. And what I'm going to do is I'm going to do a count. So in our live sheets application, count for us is just, I want to see how many of each value we have, right? So how many taxis had 1 passenger, how many taxis had 2, how many taxis had 3, and so on and so forth. That's great, but that's not really what I care about the most. I want to actually see a map, see what's going on, see where the hotspots are for these different things. So what I'm going to do is I'm going to do what I call a link. I'm going to link this data set, which has 1 through 6, and I want to specifically see all the taxis that have 2 passengers, which I'm showing here, 2 passengers. And what I want to do is I want to pull up a map, and I want to visualize where all of these taxis are being, the pickups and all that kind of stuff are going on a map of New York. And so I'm going to just drag over, I'm going to say the latitude of this map is here, I'm going to pick up latitude and longitude, and then I'm going to add these little pinpoints that appear on the map. I want to show things like how many passengers were there, the time it took to get there, and then the distance of the trip, right? Fairly simple things. I'm sure you could get a lot more interesting information in there. And you'll notice I only have, there's an 8 there, and then 2 other little dots. So I'm only showing 10 records, right, out of the 9,000-something that are 2-passenger taxis. So I'm going to up the visual number to, say, 1,000, right? I want to view 1,000 taxis. And so what this is doing is changing some filtering behind the scenes. We actually haven't done our filtering properly, so we have some outliers you saw in the middle of somewhere in the ocean. But we're going to dive into New York. Let's keep diving in. I was trying to find a good example here. And basically what I'm going to do is I'm going to find some points, click on them, and show you different information about them. So you can see that we've got some places near 65th and 66th and 64th that are 2 passengers, different trips, different distances. Pretty interesting information. Maybe you want to do more about this. But let's say now, I'm like, okay, 2, good. But I want to see 2 and 3, right? I don't know why I started typing it there, but I want to see 2 and 3 passengers. So all I'm going to do is I'm going to change what I want to see by clicking the selection, and it's going to rerun the query interactively. And it's going to eventually give me a new map that's reflecting both 2 and 3 passengers. And so I'm going to start diving in to try to find the 3. I'm going to make a mistake and go to the wrong one. I'm going to find some 2s and have to find a 3. But basically, I'm looking around, and you'll find some 3s in there eventually. But it's a way to kind of interact, right? So you're taking your data, you're looking at some various fields in your data, some structured data, and you can look at it in a map, you can look at it in other scenarios. This is all static, though, right? So I'm going to keep diving in and find some other ones. And so this is an example of live sheets working on static data, which, like I said, was one of the 2 cases we need to handle with our prototype, which was live sheets, a line of business user tool. But we also want to handle streaming data, and that's where you want to use Spark streaming, right? We moved away from Storm. Spark streaming looks like a very nice option. So now we're going to jump to streaming. So in the same application, with the same kernel as the backend, using the same APIs, I can do streaming. And it's basically going to connect to Kafka. This is running Kafka stream in the backend. I had to accelerate a little bit because we have some bootstrapping code that runs, so you might see the time kind of jump a little bit at times. Same taxi data, still got a bunch of passengers. I'm going to do a count on this passenger count to show the different totals for the passengers for the taxi, right? When I do this, you'll see that the data is actually going to keep updating. So it's going to start the computation underneath, and this is actually using Comm underneath, by the way. At the point when we finished standing up live sheets, that bootstrapping I was mentioning, that's done all the code compilation we want, and now it's just using Comm to reflect the queries that we want to do. And so here I'm going to show a bubble chart. It's got some different passengers, and they're changing as the stream comes in. But let's say I don't care about the 1-passenger taxis. That's something I just don't want to see. So I'm going to filter that out, and you'll see over time that it's going to gradually filter out the 1-passenger taxis through the table first, and then eventually it'll trickle down to the bubble chart. But it's just a way for us to show the interaction of Spark, showing that you can do pretty nice interactions on top of a Spark cluster. And this is, once again, using the Spark kernel underneath. Code execution and Comm APIs. That's all we've got going underneath. And so this is an example of 2 different aspects. Historical data, existing taxi rides. Streaming data, new taxis coming in. So now I'm going to introduce one other application we've got, because I'm sure there are a lot of people out here that say, well, even with the client library, I just don't like having to embed a client library. Maybe I'm not even using Scala. I want to use it in, say, Python or some other language, right? So of course, people think instantly REST. REST is the way to expose it, make it be language agnostic, and meet a more standard fashion. So we have that. I'm just going to show one example of our REST server. This one basically takes what we call data sets. There's small wrappers around RDDs, but the REST server can work on both of them. And I'm actually going to just poke at an existing data set. You can do other interactions. You can run functions and stuff as well. I'm just going to basically do a RESTful query, which I'll show you as well, but this is doing it behind the scenes, getting the same taxi data. Actually, no, I think this is abandoned vehicles in Chicago or something, but still data through Spark. It's doing RESTful queries that go against the Spark kernel. And of course, I'm going to do something more specific, like maybe I only want to see the open statuses on these abandoned vehicles, right? So I'll just provide a little query here, submit it, and eventually you'll see a table that populates it, just showing 5 open requests. And that's great. And of course, just to illustrate, I'll go up here and also show you that, yes, this is a RESTful endpoint. We just have a nice little UI to kind of examine these things without having to manually type the RESTful endpoints. Same kind of thing. You specify a kernel. You specify the data set you want to work with. And it's just query parameters here, so they can be cached by the browser, right? Very simple to use. We use it for several other applications. In fact, we gave a demonstration at ZenCon I think it was last year, and it used the RESTful server underneath for a PHP application, right? So we've used these kind of things for other applications as well. This is going to basically give you some JSON back that contains the schema of the data set along with X number of records. I think 5 is what we said. So that's just another example of something that can fit on top of the Spark kernel. So what we kind of treat the Spark kernel as a foundational component to Spark, right, is the missing interactive piece that Spark does not have. You've got being able to submit jobs, which is fine. You got being able to do JDBC, which is good for SQL. And you got the Spark shell, which is very nice for early starting. But when you want to move that further, the Spark kernel is what we found to be very helpful. So those are some of our demonstrations. We've shown that you can extend your kind of flexibility by being able to send code snippets. You can run jars the same way, as well as doing Comm API to reduce how much code you're compiling, as long as define a more standard interface, right? So you don't want to just have code snippets as your main API. Define some Comm APIs, and you basically have JSON-type structure that you're sending back and forth. Pretty simple to do. We're using that for all of our live sheets, RESTful, and basically all of our applications underneath are using the kernel to do this. So there are two things that we want to add. So I've been mentioning Scala, and more than likely there's quite a few out there that want to use Python, or maybe one of the other languages. So PySpark support we've looked at for a while. We've done tests in the past, and we're looking pretty closely now to add PySpark support as a quick addition to the kernel. Same API, same way to use everything, but now you can use Python as well. And then also, there have been quite a few people that have come up to us and said, you know what, IPython is nice, but I also really like Zeppelin. Zeppelin's this Apache project, similar to an IPython notebook, but just goes different routes. It started, I believe, with Scala, and they've added PySpark as well to theirs. And so we gave it some thought, and we said, you know what, that would also be an option to have, because the kernel itself is not supposed to be limited to one platform. It's not supposed to be limited to IPython. We found the protocol to be very flexible, which is why we chose it. And it has been. It's suited all of our needs interactively with RESTful components and everything. But there are people that like using Zeppelin over IPython for interaction. So one last little detail I want to show is I cooked this up on Friday in the span of a couple of hours. It's running the kernel as the backend for Zeppelin. How many of you have used Zeppelin? Have any of you used Zeppelin at all? A couple of you? Yep. So this is just running in place of the standard Spark interpreter. It's running a kernel underneath. So you can imagine you get all the benefits of running the kernel underneath. You can get the same kind of compilation and the Comm API and all the fault tolerance and scalability that you'd want. But now you're going to have Zeppelin run the same kernel underneath, right? It also helps to more unify, because there are a lot of different options out here to do this kind of API interactivity now. They're trying to. And one of our goals is to help unify this kind of community response. There should be one way that people can just go to and rely on for all their interactive applications. So all I'm going to do here is just kind of show, it's nothing exciting, but it's just kind of showing this is indeed running our kernel underneath. It's going to get some simple stuff like some build information underneath Zeppelin, and just do like some standard map and reduce. You can imagine the rest of the stuff is there as well. But yeah, so it just kind of shows that it's really easy to plop this kernel underneath. That's the back end for quite a few different applications. So just imagine it as the way to go through with interactive applications. And of course, I'm going to keep doing stuff. You're going to see the kernels getting started up here, all the fancy logs. So eventually, we'll get through this stuff. But that's the gist of the Zeppelin part, right? It was very easy to plop in. It stands up. I believe Zeppelin uses Thrift to stand up the kernel itself and communicate, but you can still communicate to the kernel through the Comm API and the normal GRMQ ports as well. And so I used the last bit there. So that's kind of a way to jump it in and use it right away. Obviously, there might be some more work that needs to be done on this. But overall, pretty simple to do. This kind of shows how the kernel can be plopped into pretty much anything and expose more functionality than just interpreting code. So that's basically the end of all the little examples I have, right? So we've seen live sheets, we've seen various instances of the IPython notebook, we've seen a RESTful server, and Zeppelin itself all running through the Spark kernel underneath. So in summary, there's only a few things that we kind of focused on here, right? So the goal was to provide an interactive API. I wanted to enable applications to be able to interact with Spark in a very fluid manner. And we think we've done this. We think we've provided a responsive API. Its responsiveness is in milliseconds to seconds, depending on how complicated your computation is. Obviously, if you do very intensive computations, they'll sit around for a while. But we've had, when we've done some really badly written computations, they've taken hours, but normally you want to fine-tune those. But in terms of the kernel, it handles it like a champ. There's no problem there. We've exposed two main ways to communicate with the kernel via submitting code requests and jars. as well as using the Comm API. So programmatically friendly, you can define the API very easily, tailor it to your needs. And of course, another aspect is we've implemented the IPython protocol, meaning you can drop this into an IPython notebook, no extra work needed, other than just saying, here's a kernel, and go use it. And yeah, that's pretty much it for the summary. We feel like we've accomplished what we wanted with the interactive applications. And we feel like this is a pretty good answer to one of the missing links in Apache Spark, which is there's not really a way to easily interact with a Spark cluster. You can submit jobs, write out the results to HDFS or Cassandra or Postgres. You can use REST endpoints to try to get some data back. But when you want to start doing dynamic queries constantly, and you want to send data requests fast, and maybe you want to send it to multiple clients at the same time, it's easy to do that. In fact, some things I did not mention here. So out of the box, you can actually connect to a kernel with multiple clients. You're sharing the same namespace, but you can imagine having one kernel that stands up all of your work, that we've done this with an IPython notebook, defining some functions, and having another application connect and use those same functions. And so there are some other goodies as well that I didn't show, along with live sheets, being able to do things like exporting functions out of a notebook and pipeline them into your data so you don't have to worry as a line of business user what your functions are doing, just get your data scientist to actually write them for you. But that's the gist of what the kernel does. That's the gist of how the kernel works. And yes, so I thank you for your time. And at this point, I'll be taking questions along with Mr. Fallside here. And thank you very much. So Spark Job Server, which I think was formerly the Uyala Job Server, right? Can you repeat every question? Okay. So the question was, how does this compare to the Spark Job Server, which I believe was formerly the Uyala Job Server, correct? So actually, that was one of the options we looked at before we built the Spark kernel. At the time, it actually was lagging behind in version as well. But the Spark Job Server is RESTful, and that means that its only options are you submit jars, you run those jars that are your Spark computations, and you get results back for those jars. Which means that, yes, that's good. You can use REST. You can get the JSON back that represents your data, but it's not interactive enough for our needs. As I was explaining at the beginning, what we had to do is we had to rebuild jars every time we wanted to change the computations and the jobs we wanted to evaluate. So basically, if we had to use the RESTful server, we'd still have to rebuild these jars, ship them over. Rebuild these jars, ship them over, and keep doing this. And it was taking the order of minutes to do. So if you're doing some simple or long-run job, and it's just one or a couple, and you don't really care about it being that interactive, the RESTful server will work. And we've demonstrated running a RESTful server on top of our own work as well. But it's not interactive in the terms of the quick response, like request, reply. It can't run code snippets as well. So the RESTful server can only run jars that I'm aware of. And also in terms of libraries, I mean, you've got RESTful, but you still have to build the RESTfulness into your applications. We also have the client library exposed to be able to have more of an abstraction away for that aspect. But yeah, basically it boils down to you have to rebuild the jars, run them each time. It's not really that good for, say, the pub submodel that I showed. You have the publisher that's going to send out, say, comm messages, broadcast them to all the clients that are listening. With REST, it's not really that easy of a thing to do. You could have some sort of API that listens and has a job ID you could query, but overall, it's not as interactive as we like.
We'll use a microphone so you don't repeat the questions.
Okay, that works.
Yeah. Hi, I'm wondering about a particular scenario. So say you're in an IDE with a large, Scala project doing some Spark things. You submit a main, and halfway through it blows up, but before it does, it has some things cached. Can you change something in your IDE and have that change run on the things that are cached, or is that something that's workable?
So you start an application, it's going through doing tasks, and in the middle, let's say it's done some maps and reduces and it dies. Is that what you're saying? Mm-hmm. Yes. So because the Spark kernel acts like a Spark shell, if you're in the middle of a Spark shell, right, you're running some tasks and it dies in the middle. That's part of the Erlang's pattern I was talking about, right? It will protect against that state, so you'll still have the state you already had, and you can continue from where you left off. So yes, the answer is yes.
Cool.
Broadcast as one of the facility. Now, what kind of, if you look at the third slide or fourth slide somewhere in the beginning, IOPub.
Yes.
So is that used for broadcasting, and what is the use case in this context?
So imagine one case is, suppose you have multiple clients that are listening for an interaction. Suppose you have some data set you want to work on, right? And so actually, suppose you have multi-tenancy. You have multiple people that are listening for data that's being updated, right? One person updates the data, and everyone wants to watch as that data gets transformed. So that's one way to share that kind of interaction. The broadcasting is also a way to share, let's say, you have listening metrics. So Spark itself provides a listener API to get metrics about what tasks are being executed in a cluster, what the state of those tasks is, what kind of jobs are being run, the stages, all that kind of low-level metric information. You can imagine as well, this thing we've looked at that I forgot to put on the list of to-dos, you can imagine that being hooked into the I/O pub such that every client that's listening, if they want to get the latest metrics of what the cluster they're connecting to, what its state is, they're getting that broadcasted via the I/O pub, right? So whenever anyone does an interaction on the same cluster, they can see the state of that cluster. So it's a way of kind of sharing any kind of state transformations that might affect another client connecting to the same cluster.
Does that answer the question? Yeah, thank you.
So do you have a single Spark context on the JVMs, or is it multiple JVMs, so each one a different context? Just think about a multi-tenancy situation. Are they sharing the same context or not?
Yes. So presently, they are sharing the same context. When we first developed this, Spark did not allow you to have multiple contexts in a JVM. I know there's an option that supposedly allows you to try this. I haven't actually tried it myself. But the idea is that if you want to have multiple contexts to isolate resources or something like that, you create multiple kernels. They're not that heavyweight. You just stand them up and can facilitate communication that way. But yes, in practice, if you connect multiple clients to the same kernel, for now, they're going to share the same Spark context in the same namespace, because we haven't done any namespace isolation. But yes, it's a one-to-one mapping. One context per kernel is the mapping that we have right now. Here's another, no?
So how do you handle security from the application through?
So at the moment, because we are emerging internet technologies, we mostly make prototypes. The only security, which, like I said, I wouldn't really consider it security, is that signature checking, right? For now, it's just whatever ZeroMQ offers, which in this case, I believe ZeroMQ at the moment does not implement the curve type security of higher level stuff, so you probably have to protect against that in terms of who's actually going to access and use the kernel by better protecting against that. So the answer is there's no security on the ports themselves. They do, in the IPython protocol, they do specify signatures to verify that clients that are communicating that don't have the same secret key that was given to the kernel are not valid, and the messages will be ignored. And they do have the concept of a user. They include a user in each of the messages that's sent, so you could technically guard against unknown users that are being used, but there is no built-in security to the messages themselves, or to the protocol itself, right?
I have a question.
Yeah.
How has this been in terms of interacting with IBM's customers? Are any customers on the roadmap to be using this? Are they using it already? Or how is the technology transfer working, just kind of like plugging it into the bigger IBM ecosystem?
So this is an underlying sort of building block, right, which enables applications. And so to the extent that we're sort of prototyping applications with customers, then this is one of the building blocks that gets used underneath. So the live sheets technology that Chip mentioned earlier relies on the protocol, the Spark kernel as a sort of the intermediate block between the application and the Spark cluster.
For example, live sheets is one of our more flagship prototypes at the moment. It uses the Spark kernel underneath, right?
And is live sheets something that's being used in applications with customers? Is that the connection?
Yeah, it's starting to be.
Yep.
Yeah.
Cool.
It's also on the, we have a cloud piece for Spark, which was announced in the last couple of weeks. And so it's in, the kernel is in there as part of that. So anyone who uses the Spark as a service gets to use this as part of the Scala notebook.
So this seems very geared towards interactive, the interactive nature. Is there any automated use case that you guys have found for this kernel?
So automated in what sense? as a sort of a production
so
sort of long-running job or something like that?
The algorithms engineers have 400 different variations they want to run. So would they use this, or is it more advantageous to have our own implementation or something?
But the kernel is really a sort of a pass-through mechanism. I mean, it doesn't. I mean, whatever algorithm gets implemented, if I'm understanding your question correctly.
Picture the kernel as more of a remote gateway into Spark. So where you might implement your algorithm and use Spark submit to ship it over and evaluate it, the kernel can do the same thing, basically. All it does is provide more ways to tap into inspect your algorithms as they're getting processed, to be able to kind of tweak them if you need to be able to tweak them. Say if you have some sort of machine learning algorithm that has quite a few different parameters you want to tweak, right? And as you're running it, you might want to try to change some of those, right? You could do something like that. But the gist of it is whatever you would normally do in, say, a Spark submit or a RESTful instance or JDBC or any of those things, right, you can do through the Spark kernel. It just provides different ways to do it, right? Evaluating code, running jars, using Comm API. So in the sense, let's say you didn't want to change anything, you want to use Spark submit to submit your job that's going to run that iteration, right? You can just send the jar over to the kernel and run it too. It's just a way to proxy it around and provide more avenues of interaction.
Hey, Chip. What's the future plan for the kernel?
So
or is there a future plan?
The most recent options are adding PySpark and looking into Zeppelin, because we've had several people talk about Zeppelin. We've had other discussions as well. We've had quite a few things we've tweaked. I'm not sure which ones I can really delve into yet, because some are still based on prototypes that we're still trying to see what people want to do. We've looked at things, like we've looked at other languages. We've looked at, what else can I say? We looked at a debugger at one point for this as well, and that might still be in the mix, but it depends on what kind of customer. It really depends on what the customer needs, right? We're working to see what do our prototypes need to make the customers want the prototype. So I really say that, I could say something today, and then a customer comes in tomorrow and says they want something else, and that will kind of target what we do. But once again, this is open source, so it's no longer just us developing this, right?
Again, two questions. So one is, if you're using Spark REPL, that means that it's either Spark standalone mode or young client mode.
Yes.
So, and since you only have one Spark context, people can write a very bad queries to aggregate directly on the driver, so that crash the driver. So that's my first question. How do you handle that case?
Sorry, I missed the latter half of the question on that.
So because people could write a very nice Spark code, and they could write a bad Spark code. Mm-hmm. If they write a bad Spark code, they aggregate everything on the driver. So essentially, you crash the JVM, so your drivers died and everybody's died because they only have one Spark context. So how do you handle the case like that?
You're asking how you handle the case of a context dying?
Yeah, because the memory out of the memory, for example.
So you're saying if someone has kept contributing terrible code that caused you to run out of memory or something like that?
Yeah, on the driver.
Well, we are using the ACA actors, so the idea would be that you'd abstract away this kind of problem into the ACA actors. Now, currently, they're all running in one JVM. So if you took the bare bones, keep in mind this is a prototype, you took the bare bones, you're going to crash your kernel. Now, we have the model of kernel goes down, we bring it back up and keep going, right? Through things like Mesos are running it underneath inside a Docker container. But with ACA, you can actually have remote actors. So you could think in the future as another future goal, put your Spark context and that kind of interaction in a separate JVM that if it goes down, you bring it back up and continue from where you left off. Now, if it was a case where it doesn't die from something like an out-of-memory exception, you can also just cancel the job, right? You can send requests to Spark to cancel the job, and then it's up to Spark. If Spark can't handle canceling a job, that's a different problem. But if it's the case of a job eating up all your resources and you need to stop it, you could always do that cancellation. And that will happen separately in parallel to you executing code.
I see. So we handle it, we're just using young cluster mode rather than young client mode. My second question is, I invited the Jupyter's people to give a talk about 3 or 4 weeks ago about the IPython notebook. And then we asked the question about the IBM kernel, Spark kernel. And they basically saying that actually you don't need to do that. They can easily wrap into the Jupyter's. So I just want to hear your comments on it.
So they're probably thinking of PySpark. With IPython and Jupyter, the PySpark implementation, in fact, we demoed this in the Spark Summit last July. you can easily just embed that into a notebook, right? And it will run out of the box, which is pretty nice. It's a good start. But one isn't expose the APIs in the form you'd want. It's just they implemented a protocol, right? But you can submit code too. But you don't have some of the flexibility, like the Comm API doesn't provide the kind of interaction you'd want. So there's more targeted towards widgets. Furthermore, this is Scala-based, right? So I would argue against them that you can't wrap magically a Scala-based shell that easily. They might think you can, and it might be able to do some code execution, but I guarantee you it won't be able to handle at the level that we've got here with this one. In terms of scalability, right, the actor scalability, in terms of the Comm API flexibility, and the client library we already have exposed as well. And also in terms of, let's say we add PySpark down the line and other things down the line and other functionality, it's going to further and further devolve from just being a simple PySpark wrapper or one of those other ones.
Thank you.
Mm-hmm.
Hi. Is there any facility to clean the data? I think in the demo that you showed, you used cleaned data. So
like the Lightsheets one was not fully clean though, right? Because I had some outliers that were in the middle of the ocean, you noticed at the beginning. But yes. So what about the clean data though?
No. Is there a facility to clean the data?
So the Spark kernel is just allowing you to submit any code you want, any jar you want, Comm API communication. So where you'd normally clean data in, say, Scala, you do the same thing in the kernel, right? You'd load your data in, you do the cleaning like you normally would, and that's how you do it. That's how we typically do it in our code, right? So we have a DSL in Livesheets that I didn't actually show in the video, but if you clicked on one of those figures, you'd see the code that was actually generated, and some of it handles trying to clean some of the data, right? But no, don't think the kernel is some sort of magical API that does everything for you. You just still do the same interaction as you would with Spark Submit or maybe JDBC or one of those other ones in some form or fashion. It just provides more interactive ways to do it. So suppose that you're running your job, and suppose you have an application, you want to write some snippets of code first, loading your data, then you can write some cleaning code, and that can all be included into some client-side execution. So you write some of your code in let's say like an IPython notebook that does your cleaning. You can just take that same code snippet and put it into your client application that sends those same code snippets to the kernel, right? It's just a different way of executing your code and evaluating on the cluster, but it's still just doing code execution on the cluster. So the same way you'd filter with any other way, you do the same way here.
Thank you.
All right, let's do one more question.
Okay.
Hi. I actually was wondering what the use case for the STDN is in particular, but what my understanding is if you have like a Kafka stream somewhere, so you want to see the data being fed into a client app, you would use STDN, is that right?
Sorry, use what?
You would use STDN to pipe the analytics data.
Oh, the standard N one.
Yeah, standard N.
So the standard N one, I think more of it's the opposite of a shell. So shell, you make a request, like execute code or something, it gives you a reply back. Standard N would be the opposite. So you'd make a request to the client saying, hey, you did something like, say you want to make a generic function that will go pull down data and then do a bunch of operations on it to clean it up, maybe parse it from a CSV, do a bunch of cleaning, but you wanted to make it take any kind of destination path, whether it be HDFS, HTTP or something. Standard N would ask and say, well, tell me the actual URL, right? So in terms of your case of, sorry, what was your case that you were talking about? Streaming data. So streaming data, I'll actually explain, because I didn't go into too much detail of how the Livesheets worked, right? So when you saw that streaming data, here's exactly how we did it. Bring up the client library, execute some code that loaded our data in, register a Comm API that did the operations we wanted to do, such as doing counts, doing operations that we wanted to say, like, give me the latest what's a good example, actually? Are any of you familiar with RDDs? Streaming RDDs, the dstream stuff, right? So all this was doing, the streaming aspect was, it was doing a for each RDD on a dstream. Inside there, doing a take of, we said 10 was our limit, but you can change that because that was part of the Comm message that was sent. It told you what the limit was. And so each of those for each RDDs, we were doing a Comm send message with the data back, right, in a JSON format. So that was the case of using Comm to quickly send the queries, but we just set it up once, compiled it once with the for each RDD on the dstream, and that just gets evaluated over and over with the compiled code, sending the messages back as JSON data via the Comm channel. So that would come back over the I/O pub to the client, the client would get it and then have a callback it could use. So in terms of live sheets, it has a callback, says I got some data, I'm going to visualize it. I got some more data, I'm going to visualize it. And that's when you'd see the table scroll each time, was it was re-updating the data. And that's why it would reflect all the other things down the line too. So that was all Comm API.
All right, let's thank Chip again.
Thank you.
And let's thank Galvanize again for hosting us in a great space. And then, before you go, I just want to make 2 announcements. One is that the call for submissions or proposals for talks to the Spark Summit Amsterdam ends next week, today, or a week from today. That's the 7th.
Next week today.
A week from today, on the 7th. And so if you want an excuse to have your company fly you to Amsterdam to speak at the Spark Summit in October, so the second announcement is if you're going to be in Europe, in Amsterdam in October, we would love to see you October 27th, that's 4 months from now, at the next Spark Summit. That's about it. Look forward to seeing you at the next Spark meetup. And until then, keep using Spark. And if you have a venue or a talk that you're interested in hosting or presenting at a Spark meetup, come and talk to me. All right, thanks a lot. See you soon.